Okay, welcome ladies and gentlemen to this next regular oral session. My name is Michael Himmelsbach from the University of the Bundeswehr in Munich. And this next session will be all about sensors, both virtual and real. The first speaker will be Philippe de Sousa, and he's going to talk about modeling and validation of a new generic virtual optical sensor for advanced driver systems prototyping. So please welcome him.
Okay, so ladies and gentlemen, thanks for attending this presentation. So let me introduce myself. I'm Philippe de Sousa from the company Civitech, which is a small spin-off from the French Institute IFSTAR. And I'm here to present these results since the main author of the document, Dominique Gruyé, was not able to attend the conference, very sadly for him. So most of this work has been done within the context of a French-funded project, Emotive. So, to locate the context, when you want to test some ADAS and prototypes, this is generally what you go for. You have a vehicle embedded with different kinds of sensors, such as odometer, inertial central, radar, camera, rangefinder. Okay, and of course, you got onboard processing, and this allows multiple applications, okay, such as road marking detections, obstacle detections, and things that you're already familiar with. Now, of course, when you have this kind of approach, okay, you get useful data, but there are certain problems, okay? You're aware that real ground tests have some important costs, can cause much delay, required to have people available, sometimes the right weather conditions, and often have some repeatability problems. Okay, so of course, now that's something which is coming up. It's the question of having virtual test driving. So this virtual test driving can be very wide. It can concern several parts. It can concern functional requirements, okay, about what the design requires, about what are the system requirements itself, the environment requires. It can be an answer to some technological questions, okay, about what kind of sensors, what vehicle, what control command algorithms, and so on. And virtual testing is also supposed to answer some quality requirements, such as the design constraints, the reliability of the system, and of course the performances. So what is expected from virtual testing is to intervene in the sensor calibration and validation stage, in the functional validation, in the system validation, and in the overall quality validation. So of course, this is really a wide subject, and in this paper, I will talk specifically about the camera modeling. Why? So before coming to the sensor itself, it's how to formulate what are the challenges that you face when you want to go to virtual testing. I mean, if you're used to working with prototypes, and I come and tell you, okay, now you'll work with a simulator, the first thing you want to ensure is, will the simulation be reliable enough and to be meaningful and to help, of course, to gain time, to gain costs, and so on. So perhaps there is not today one solution that has been adopted by everyone, but here we propose some solution to have a robust approach to the problem. So in our opinion, in our vision, the first point is to have a strong realism of the simulated environment and of the scenario's behavior. Okay, you want the simulated environment to be as realistic as possible and to have plausible events that are occurring. The next main point is having a reliable dynamic vehicle, model for the vehicle. Okay, that's quite obvious. And the last point we see is that you need to have a physical approach to sensor modeling. Okay, why this? Because of course you can expect sensors to improve gradually, but algorithms are also strongly improving. So to be able to test very fine conditions, you need to have a very fine approach in the modeling too. So the work was focused around the ProCivic platform, simulation platform, okay, that accepts various kind of sensors. And the focus of the platform is to verify by simulated prototyping that ADAS systems function. But just have a look at these images on the right. Okay, one thing, comes from mid or low quality cameras, okay, that are available on the market. You see strong defects on the camera. And of course, these kind of defects, if you don't take them into account at early stages, okay, they can probably ruin your system, the performances of your system. So the real focus of this platform is to highlight when systems do not function, rather than show that they function. So it's supposed to help to analyze failure causes and to be able to interactively test some setting, okay, have some variation on the scenario parameters, and to improve like that the quality of the system. Now, of course, this can be applicable to different technologies of sensors, but here, as I mentioned, we focus on the optical model. So the chain has a very basic requirements, let's say. That means we expect it to be a physically driven model. Since to model a camera, it must have very realistic information from the environment. Okay, this is obvious, but what is sometimes less obvious is that the optical camera information is very different than simple eye information or than video gaming information. Okay, meaning that the dynamic of the images of what the camera sees from the scene is extremely strong, and camera sees in a spectrum range that is very different from the human eye. So another main requirement is that we want not only to model specific cameras, but to be able to model a broad range of cameras that are today on the market, and have an architecture that allows to anticipate the technology evolutions. So this is why we had a very generic approach for the model. Okay, so the two main operators of the model are a rendering stage, that is the transfer function between an abstract environment and the camera. Okay, the output of this stage is the luminancy seen by the camera. And the second stage, of course, is the camera model itself. That means the transfer function internal to the camera. And this allows to produce simulated raw data. So for the first part, for the rendering stage, one main aspect is, of course, the lighting. So as seen in those pictures, lighting can have a very strong impact on images. Okay, you have sometimes sun grazing, or multiple lights from a car in front that completely glare. So in the simulator, were developed specific models for light sources, allowing to have, of course, several light sources that can each have their own angular diagram. Okay, that's simply the intensity description of the light source. This is measurable with equipment that suppliers generally have. This render also allows to compute complex shadows. Okay, this is, of course, related to the needs for image processing, where sometimes shadows will cause false alarms or bad detections. And of course, the model takes into account any kind of sources, such as sunlight, car headlamps, street lamps, and so on. Now, of course, this is for the light source description, and you need a second part is the surface properties of the objects in the scene. So we used a BRDF modeling approach. BRDF for bidirectional reflections distribution function. Okay, it's just a 4-dimension function that says what intensity goes in what direction with so and so enlightenment. So there are several ways. This has been very debated in the literature. Okay, so we adopted parametrical models rather than having BRDF tables. Okay, the reason is quite simple, is that we wanted to avoid having huge databases of BRDFs, and to be able to tweak, some physical parameters of the surface, such as the granularity and so on. So we implemented different BRDF models. Okay, This I won't say much on them since this is quite well known, especially in the computer graphics branch. But just to say that these models each have their own range of validity. Okay, Blindfunk is well known for plastics. Fortune is quite good for all retroreflections, and Cooktorrents for metals and for those kind of behavior. So this on the right example just of views from the simulator. On the top, it's an integration of some real headlamp diagrams, okay, on a vehicle, okay, with the road surface having some arbitrary reflection properties, and down is just an illustration of the shadowing of our two light sources. Okay, so what you need to see on the down image is that the shadows are distinct. Now, that was for the lighting, and of course in the rendering stage, we have to take into account weather conditions. So for the modeling of the rain, which is one main condition because it occurs quite often. So of course, one first part is to change the surface reflectance of the wet surfaces. Okay. Then next, to have a model for the rainfall. Even though the raindrops that are falling are usually not directly visible, they cause a loss of contrast in the scene. And eventually, a model for raindrops that are gathering on a flat surface. So for the rain and now for the fog modeling, the models, the standard model today for day fog is the Koch-Meade attenuation, okay, exponential attenuation of the contrast. Some works have been done around the simulator for heterogeneous fog, okay, based on some Perlin noise distribution. And a last model was to define the fog locally to the scene. So on the left, of course, you have a few examples of rendering with these effects. Now to go to the camera model. On top left, you have a synthetic summary of the model. That means it takes the spectral luminancy. And we start like with a near perfect image, okay, a sharp image. Then we gradually add some defects that are added, such as blocks. Okay, the top stage allows to compute the luminancy that arrives on the sensor plane. Okay, that means that this luminancy has been affected by the optics of the system. And once you have the luminancy on the sensor plane, you have to model the sensor itself, the photo response, and so on, and the electronics. So to implement this, the technical solution we adopted is to have a way to manage post-processing filters. Okay, this allows to model really in a very flexible way the components of the system. That means you can have general components or very specific components to suit so and so specific camera. So this is the trade-off that we obtained between accuracy and flexibility. And of course, with this kind of approach, it's very easy to remove or to add some rendering, some modeling stages that are specific to certain models or not, or to certain technologies. Now just an overview, quick summary. I won't go very into depth of this. So for the optical defects, mainly, let's say that we model lens distortion, okay, with two approaches, polynomial approach or a map approach, vignetting, depth of field, chromatism, and so on. And for the sensor itself, well, taking into account what we have to, that means the color filter array or a generic color transform function, different sources for noise, that means it can be the read noise, the photonic noise, sensitivity, non-uniformity, and so on. Blooming for the sensor, the kind of shutter, if it's a CMOS that is subject, for example, to a rolling shutter, and things like gain control. Okay. Of course, once this model has been developed, one interesting question is how to validate it. So one procedure to validate the model itself was to use a calibration benchmark. Okay, the choice in this case has been made to use a DxO benchmark that is quite recognized in the world of professional photography. So in the context of the Emotive project, well, there had been a benchmark that was bought and used for this purpose. So now in the procedure, you have your real benchmark, and we added a simulated benchmark. So then the calibration is made on the real benchmark. You obtain parameters, and then you can reintroduce them into the simulated benchmark, okay, to set up your camera inside. So then what you can do is compare the results. This DxO software has the advantage of giving some specific metrics to evaluate the performance of different things. That means it can be the focal length throughout the field, it can be the FTM of the system. So this allows to make a comparison between the model in the simulator and the results coming from the real camera. So if we are presenting, of course, this to you, is that the results were very positive. Now, to have a few applications. The first one was a kind of high-level validation approach. That means, I'll try to get this, that we had one of our colleagues walking in front of the IFSTAR building. Okay, sorry for the video. And then we modeled the scene in the simulator, and what we did is not just say, okay, the pictures look the same, we calibrated the webcam well, that's great, but we decided to test different kind of low-level algorithms in the idea of saying, if these low-level algorithms behave the same way on a real image than on our simulated image, that means we are really on the right way. So the example you see, it's for edge detection. Another application now, which makes use of the lighting part, is an example of tunnel crossing. Okay, I'll just get the video in front of you. Okay, here the camera is in a vehicle, and when the exit appears, at the beginning it's subject to strong blooming, and when the vehicle comes out, well, it doesn't adapt fast enough. And if you look well on the left, you will see that there's a vehicle which is not exactly at the right place. Okay, that could be an obstacle. So this, of course, features different things. That means the blooming, the effects, the dynamic response of the camera. And I will just show you another application. It was like evening driving. That means in this case, the camera is on the rear of the vehicle, and we have a motorcycle that is coming up the lanes between the vehicles. So here you have various lighting conditions, you have shadowing, you have blooming, and it's again a mixture to show the performance of the overall model. That means with the lighting stage and the camera stage. Okay, so now just as a conclusion, so today these models, okay, have been integrated in the simulation platform ProCivic. Okay, that's one point. Now there are, of course, much ways to improve the model. Okay, we can be thinking of a specific operating condition. That means what happens if the camera is in the vehicle and you leave the vehicle in the sunlight for a whole afternoon by 35 degrees. Okay, that can change the noise levels of the camera. That can have some effect on the system. You can have also some particles that affect the camera response. Okay, if you have dust on the lens somewhere, condensation inside the lens or on the lens surface. And other kind of improvements could be more on the rendering stage. That means to have like water streams on the windshield, okay, by rain conditions. That's quite complex, but that's a requirement, I mean, for sensor validation. Now, with this state, we think that this is rich enough already to start to replace, in an extensive way, real testing by simulation for system validation. Okay, there are, of course, things to improve, but maybe if we can replace 30, 35% or 50% of driving with prototypes, that would already be a good success for us. Okay, thanks for your attention.
So thank you. We have time for one or two questions. Okay, there's one.
But as you mentioned by yourself in the conclusion, water on the windshield is a central problem. A couple of years I asked experts on that, and they told me that there's no simple model available. It would cost me hours of computation time to produce just one image. Are there new results? Do you have any idea how to solve that problem?
I mean, our focus on this software is to simulate in interactive time. Okay, we don't guarantee 100% real time, but by using techniques that are quite similar to video gaming, that means that exploit in a good way GPU, you really get good results. The video example that I showed, well, the complex one with about 18 light sources was generated at 6 FPS, and the other one was in real time. Okay, so of course, this is a simplification compared to very accurate like Monte Carlo techniques, but we think that for the moment, it's the best trade-off between accuracy and usability. Yes, yes, I don't understand your question. Yes, I understand that. Well, having drops on the windshield will act as lenses, okay, that of course are not in the focal plane, so it will be even a blurred image that will be kind of strange. But these are the kind of things that you can model in a quite effective way.
Okay, we are out of time for further more questions. So let's thank the speaker again and welcome the next. So the next speaker will be Mr. Hiroaki Togashi, and he'll talk about lane recognition for moving vehicles using multiple on-car RFID receiver antennas, and about algorithms and experimental results of these algorithms.
I'm Hiroaki Togashi from Japan, and I cannot believe that I'm talking such a great hall. Now, today, I'll talk about lane recognition using RFID. And yeah, two main features, I suppose. First one is using pairwise positions in estimation, and another one is the dynamic weighting function. So you please remember these 2 points. Anyway, let me start my presentation. And first, I'd like to talk about why the accurate lane recognition is required. And this recognition is used for lane keeping assistance or lane changing assistance system. And we think that a 1.5 meter localization accuracy is required to achieve these functions. And first of all, we always consider that if we can use GPS or not, and we conclude that accuracy of GPS is not enough and has some problems and limitations in the usable places. So let me move on to the existing research and already achieved higher accuracy. And first group is the methods using image recognition, and they cannot properly work if the visibility is not so good. And next group is the methods using laser scan data, laser scanner or magnetic markers, and they are achieved high accuracy like the 0.1 meters, but they are the dedicated equipment for localization, and it is desirable that the same equipment can be used for localization and information providing. So we need to find another methods. And one group is the method utilizing RFIDs. Of course, it is used not only for information providing and also for the localization, but many of the methods using this kind of technology is not so accurate or has limitation of usage places, like this one. So we proposed another method using RFIDs and achieved as follows. One point is using on-load active RFIDs and placed like here and here in the lane boundaries and road shoulders. So this is used for localization and information providing. And another point is that RFID receiver antennas. We use multiple antennas and they are placed on the vehicle. For example, it is placed on each corner of vehicles, like this one, this one, this one, this one. And also, of course, uses gyro and acceleration sensor, sometimes called as 6-dimensional gyro sensor. By this slide, we talk about motivation and some overview. And from now, we'd like to talk about our proposed algorithm and its experimental result. And before the conclusions, we discuss also about cost analysis of the proposed method. Then let me move on to the proposed algorithm. And yeah, there are so many sentences, but the point is 1, 2, 3, 4. And one is the adjust RFID positions by using vehicle displacement. And next point is that using computation of pairwise positions and from every pair of RFIDs. So if we got signal from n RFIDs, we compute the combination of NC2 RFID, pairwise positions. And these positions are merging into the final position of on-car antennas. Since a position of all on-car antenna is estimated, then vehicular position is estimated from these positions. And adjustment comes later. So from next slide, we talk about this one and this one, this one, and this one. Okay. First of all, why need the adjustment of RFID is shown here. Actual state is like this figure, and this and the signal from Q1 at time S1, Q2 at time S2, but calculation is done in time Tn. So within this duration, vehicle moves from here to here to here. It is difficult to estimate the accurate position, so we need the situation like this one, this bottom figure. And to achieve this situation, we use the vehicular displacement, like this arrow. And next step is the pairwise position estimations. That is not only achieved from the positions of RFIDs, like this 2 point, but also using the 2 distances between RFIDs and on-car antennas. So this obtained pairwise positions can improve localization accuracy. And here we obtain the pairwise positions, and so we can estimate the position of on-car antennas by like this formula. And point of this formula is that we do not assign certain value to m. Instead of assigning the certain value to m, the algorithm defines iteratively calculate this function, increasing the value of this m, 0, 1, 2, 3, and observe the change in value in this vector. And if two cross results become difference of two cross calculation of this function, it becomes falls under certain values, then we obtain the value, the position of final antenna positions, on-car antenna positions. By this side, we obtain the positions of on-car antennas, and so now it's time to estimate the vehicle position. This is using the relationship between actual antenna positions and estimated antenna positions. And first of all, First step is that taking candidate positions according to each combination of received, estimated antennas. And after taking these candidate positions according to each pair of RFIDs, then vehicle position is estimated by these candidate positions. And also, this estimated position is adjusted by vehicle displacement since last estimation. Detail is written in the proceedings, so you can check it if you're interested about it. Now, let me talk about the evaluation results for our proposed methods. And yeah, experiment done in our university. And we have done the experiment in 2 courses. One is this one, and mostly constituted from curves. And another one is this one, and mostly consisted straight and corner, and walls and buildings. So many reflections may occur in this course. And first result is a point of view from the viewpoint of statistical values, and like this figure, and on the average value, this line and this line, 1 meter accuracy, this line is achieved when the placement of RFIDs is less than 2 meters, this point. And the best case is here, and 0.7 meter accuracy is achieved for 0.1 meter intervals. And if you can see from this figure that the trend is mostly same. And the next slide is the timeline trend of data, and also cross trend, especially in the shorter placement interval. This one is the case of 0.25 meters. This is the case for 2 meters. So very close trends are found from these graphs. And we conclude that road shape does not affect the trend of localization accuracy. So let's consider how to get a better accuracy by considering the increased number of equipments or something. So first one is the effect of the number of RFIDs, and you can estimate that if you place the RFIDs more short interval, and localization accuracy may improve, but there are limitations in the number of received RFIDs. As shown in these graphs, this is the maximum value, this is the 1/4 value. There is a limitation in each values. So the received number cannot be increased indefinitely, even if we placed RFIDs with almost no intervals, but the number of received ones will remain about this point, 33 or something. Next point is the number of on-car RFID antennas, and result is this figure. And it is true that increasing number of on-car antennas improves the localization accuracy, and if we want to achieve the 0.1 meter accuracy, at least 15 on-car antennas is required by considering for these plots. Okay, let me talk about the cost of the proposed method. It is true that the cost of proposed method is expensive in the absolute value, but by considering the road maintenance cost or road construction costs, it is not so too expensive. That is, the installation cost is less than 1% of road construction costs, and maintenance cost is about 2% of the road maintenance cost. And as you know, roadside RFIDs can be used both for localization and information providing. So it is cost effective compared to the dedicated materials for localization. So we conclude that the proposed method has enough feasibility to put in practice. Okay, let me conclude my presentation. And proposed method has the two unique points. One point is the pairwise position, and another one is the dynamic weighting function. And proposed one allows the moving vehicles to recognize the lane with their in because 0.7 meter error accuracy was achieved. And this is the less than the half of the lane width. And this accuracy is mostly stable for any type of road shape by viewing timeline trend or statistical values. And the point for using roadside RFIDs is that the same equipment can be used for information providing and localization, or even more than many things. So, and cost analysis demonstrates that the method is feasible in practice because this one can be used for multiple purposes. Okay, this is the end of my presentation, and thank you for listening.
Thank you, and there's time for some questions now. Okay, in the middle.
Okay, your work is very interesting. I just wondering, is there mathematical representation to show the relationship between the distribution of the RFID and the position of the localization? I mean, if I want to make sure that the position of the localization at a certain level on the whole map, how can I optimal distribute the locations of the RFID? I mean, that gets the lowest cost. Is there any solutions?
For calculation cost? No? Placement cost?
Excuse me? And my question is that, for example, if I have a whole map and I want to make sure that the localization at a certain level, and I also want to make sure that I just spent the money the cost issue is very lost. I want to spend the very less money. And how can is there any solution to optimal distribute the RFID on the whole map?
Yeah, for the cost of installation or something that is shown in this slide, and maybe so yeah, in the absolute value, it is true that the placement cost is higher, and maybe it should be decreases, but any solution for decreasing this cost? This kind of costs? Maybe out of our research or something?
Okay, maybe you could talk about this question personally afterwards. Is there another question?
What? Okay.
Over there, yeah.
Yeah. Can you tell us something about the update rate? How often can you measure per second the distance or the localization?
In our experiment, this localization was done in every second, and it takes about, on the average, 20 milliseconds, and maximum cases it takes 80 milliseconds.
Yeah, thanks.
Okay, no more time left, so let's thank the speaker again. Our next speaker will be Mr. David Ayon, and he's going to talk about a noise model for car-embedded speech acquisition system design. And he's a resident at this university here.
Okay, hello everybody. Welcome to my presentation. I'm gonna talk about a speech acquisition system in vehicles. Right nowadays, there are many applications where speech is very useful inside the cars, and all of these applications have in common that we need to acquire a high-quality speech signal. If we are gonna take a decision based on that speech, we need to make sure that this speech has a high quality. So first of all, what we have to do is to clear this speech signal with the speech enhancement algorithms. Most of the speech enhancement algorithms rely on the knowledge of the noise field that we have inside the car. So the purpose of this work is to characterize the real noise that we have inside a car from real measurements, right? So I'm gonna start with my presentation. First is a brief outline. I'm gonna talk about the application of speech acquisition in vehicles. After that, I will tell you how to enhance the signal before to process it in order to take decisions. We'll show you the proposed noise model that we propose in this work and some results that makes the suitability of the algorithm. Okay, so first the objective, as I said before, is to acquire clear speech that allow us to make decisions about the information that we get from the speech. Several applications that we can find for the speech acquisition is driving assistant. We can give orders to the car, for instance, to make a speed limit or control the radio, wherever. So this is a speech recognition problem, but first of all, we need to clear the speech signal to improve the quality of the speech recognition. Another typical application that nowadays everyone has a hands-free device in the car is phone communications. Of course, we need to try to acquire the best quality signal in order to transmit in the phone line. Another interesting application of the speech acquiring a car could be driver security. We can detect from the speech of the driver the state of drowsiness and if the driver is suffering a heart attack or wherever. Of course, the driver should be talking in that cases, but and also it's interesting in military applications where we want, for instance, to spy or record all the speech, all the conversation of different persons inside a tank or a military car. So this could be another interesting application. So the success of all these applications relies in the robust speech acquiring. Well, this is not easy because inside a vehicle we have a different interference sources that they are contaminating our speech, right? The most important is the background noise due to driving conditions. This is always present and is the most important contaminating source. Another interference sources can be when we are talking by phone in our car. The person we are talking to is also speaking at the same time, so our microphones are recording the signal coming from the loudspeaker, so we have to cancel the signal, we have to remove it, otherwise they will be sending back to that person. And also reverberations inside cars, they are very important, and they are an important source of interference signal that we have to remove. Right, so we have different types of correlated and uncorrelated interference signals, so we need to enhance the speech signal before to process it for our final application. Right? Speech enhancement can be obtained in our system with directivity. So if we focus our acquisition system to one person, so we amplify the signal coming from this direction, and we can remove or attenuate the signal coming from the other direction. Right? This can be achieved with directional microphones, but directional microphone has several drawbacks. They are larger and more expensive than unidirectional microphones, and if we put one directional microphone pointing toward one source, it cannot be changed to point toward another source. We will have to move it or we have to install several directional microphones. However, directivity can be also achieved with omnidirectional microphones by means of signal processing algorithm with spatial filtering. Right? They have several advantages. Omnidirectional microphones are very small and much cheaper than directional microphones, and we can change the steering direction just calculating new filter coefficient for our processing algorithm instead to change the physical microphone. Well, in order to implement a spatial filter, the enhancement depends on the beamforming technique that we use, the filter that we establish in the array, and also the array dimension and the geometry. These two things here, in order to optimize the filter coefficient and in order to optimize the array geometry, we need to know the type of noise we want to reject. So this is very important when we compute the filter coefficients to know the type of noise we are trying to deal with. So we need to have an accurate characterization of the noise inside the vehicle. Right? Usually, the background noise due to a driving condition is being assumed to be a diffuse noise field, which means that we have an infinite number of spatially uncorrelated isotropic noise sources, which means that the noise comes with the same energy from all over directions. The coherence of a diffuse noise field is given by a sinc function, and here we have an example of the coherence between two microphones that they are separated 35 millimeters, right? But we have performed several real measurements in different scenarios, and we found that the real coherence between two microphones, between two microphones is this blue line here. So the coherence is much higher than the diffuse noise field. This is the red line, right? So what we propose is that the noise field inside a car is not coming from an infinite number of sources with the same energy, but we can assume that most of the noise energy is coming from several points around the contour of the vehicle. I mean, we have a finite number of uncorrelated noise sources, and we want to find where they are. Here, there is an example of the noise coherence of a noise field generated from 42 uncorrelated noise sources. That uncorrelated noise sources are in the lateral windows, in the front and the rear window, in the wheels, and in the engine of the car. And with this noise field, we get the blue line. The coherence between two microphones is the blue line, that we see that at least up to 4 kilohertz, that is the speech frequency band, when we are interested, it tracks much better the black one, that is the real measurements coherence, right? Well, then, our proposal method, what we have to do now is to find a finite number of noise sources that they are uncorrelated and they are producing the most part of the energy inside the car. So first of all, we have to define a measure of the source correlation, and after that we have to make a search algorithm in order to find the position of the sources along the contour of the car. So well, if we have a set of M microphones, YE from YM, the cross correlation between two signals, between two microphones, is given by this expression here. We can normalize the cross correlation between the two microphones, just dividing by the energy of each microphone. And the average cross correlation between every pair of microphones can be calculated averaging this function here. Well, this can be calculated from the time frequency domain. When we work with speech, we always work in the time frequency domain because we cannot analyze a long period of speech signals at the same time. We have to window the signal. Well, so this correlation function can be approximated with this simple expression in the time frequency domain. In matrix notation, set K is showing the cross correlation function between two microphones in the for the frequency K. And this expression, the normalized cross correlation, can be approximated from the time frequency domain. But this gives us the average cross correlation of the microphone recording. But what we want is the average cross correlation of the original sources. Well, our signal model can be described with this expression here, and here in matrix notation. We have M microphones. We have S original sources. And this B matrix is going to be the mixing matrix, which represents the channel between the microphone 1 and source 1 and so on. So this corresponds with the microphone responses between each microphone and its source. Well, if the number of sources is lower or equal than the number of microphones, we can invert this matrix and estimate from the recordings, we can estimate the original sources, where W matrix is the pseudo-inverse matrix of the original mixing matrix. Well, if we define now set prima as the cross-correlation between the original sources instead of the cross-correlation of the recordings, just making use of this expression, we can estimate directly from the recordings the cross-correlation of the original sources. And this average cross-correlation of the original sources is going to be our cost function. So now our purpose is to find a set of microphones that minimize this cost function E here, that they are going to be the microphones that are less correlated. Right? So we have performed measurements with 8 channels. So we can only estimate the position of 8 sources, because otherwise we cannot invert the matrix we saw previously. Right? Well, if we want to make an exhaustive search, we will have to try all the possible 8 combinations of position of sources along all the contour of the car, which is a very tedious problem. We cannot try all the possible solutions because there could be an infinite number of combinations. So we propose to approximate the optimal solution with an evolving algorithm. So what we have done is first to discretize all the possible space. This black rectangle will be the position of the microphones. So we have discretized all the azimuth angles in a grid of 420 possible source position in a 2 meters range, with speed up the searching process. We can pre-calculate the microphone responses of every source position with every microphones. With a room convolutive model, we can estimate the microphone responses, so we can estimate the mixing matrix and we can invert it in that case. Well, so if we only have 8 microphones, we can estimate 8 sources and we can find the mixing matrix and estimate the source cross-correlation value. Well, the evolving algorithm we have implemented has the same steps. We start with an initial population of 1,000 random candidates. Each candidate solution contains a combination of 8 source positions. Okay, after that we evaluate the cost function, the average cross-correlation, source cross-correlation for all the individuals of our populations. After that, we make a selection process. We select the best 10% of candidates. After that, we have to generate a new population for the next iteration. So the remaining 90% candidates of the new population are generated by random crossover of the 10% best candidates. And after that, we apply random mutation to the whole new population, but except to the best one, in order to keep always the best solution in the population. And this process iterates until 100 generations are reached. So at the output of this algorithm, we will have the position of 8 sources. Here we see an example where we use recording from normal driving conditions, and we got these 8 sources. This will be the microphone array that, in our case, in our recordings, the microphone array was placed in the dashboard, more or less when the radio used to be in a car. And we got that most of the noise, I mean the sources, depending on the size and the color of the source, has more noise. So most of the noise is coming from both sides, that they could be from the lateral windows, and this direction can be from the rear window. And these two here, we think that it's coming from the dashboard, because when we make the measurement, we found that there are a lot of vibrations that the microphones are recording from the inside the dashboard. And here, You have another example, but now we make the recordings with the window of the driver open. So now we see clearly that now this window is open, so all the noise is coming from this window here. So now these are the predominant noise sources. So with this experiment, we made sure that our algorithm is working more or less. So the conclusion we get with this work is, first of all, that the diffuse noise field is not entirely true. So that motivates to find another noise model. We propose a novel algorithm, a novel noise method. The result that we found support the suitability of our algorithm, but however, we are only using 8 microphones, so we can only estimate the position of 8 sources. So it will be interesting to use more microphones in order to find a higher number of noise sources. And this is all. Thank you for your attention, and if you have questions, you're welcome.
Questions? There's time for some of them. Okay, here in front, on the right.
Thank you very much for your interesting presentation. So far as I remember correctly, you mentioned that you will use beamformer for denoising.
Yes?
But you tried it to locate the source, noise source location, not only for direction but also the distance or depth. So what that kind of information will be utilized for the later denoising process?
I mean, this is done to characterize the noise. After that, when we design the filters, you will design the filter to the coefficients to be optimized into one direction. But when you design that filter, you need to know the covariance matrix of the noise. So this is done just to know the matrix of the noise. You know, after that, you optimize the filter just focusing in one direction, the target direction. You know, I mean.
So you can more efficiently design the beamformer by utilizing the distance information. Is that your idea?
Yes, of course. If you know exactly how is the noise, you will optimize the coefficients properly. You know, if you are missing something in the noise model, the coefficients are going to be optimized wrongly. You know?
Okay, thank you very much.
So another question, anybody? No? Okay, I got one. So this evolutionary algorithm you use for searching these positions, is this algorithm capable to operate in near real time so that you can adapt to new sources?
Not in real time. It's very fast because we make a grid of possible solution position, but not in real time. Anyway, I mean, once you have characterized the noise, I mean, you can slightly recalculate the filter coefficients, but not do this analysis again every time. You know, I mean, it doesn't make sense. You know.
And did you try like different roads when you called
yes,
your
we made
data, like bumpy roads and?
Yes, we made recordings in conventional roads, in the motorway, and with the windows open, closed. And
okay, thank you.
Well, okay. Thank you.
So the next and the last speaker of the sensor session will be Oscar Ciordia, and he will talk about an accident reproduction system for the identification of human factors involved on traffic accidents.
Good afternoon. Welcome to the last talk of this session. My name is Oscar Ciordia, and I will present the work Accident Reproduction System for the Identification of Human Factors Involved on Traffic Accident. Let me introduce myself. I'm a PhD student from the Rey Juan Carlos University and member of the Face Recognition and Artificial Vision group. Our group is working in several research lines related with face recognition and pattern recognition. At this time, on the intelligent transportation area, we are focused on the study of driver distraction. The main objective of our work is the development of an alert system for the timely notification of imminent risk situations. Driver distraction could be divided in 3 main categories. Manual distraction, when the driver has a bad hand's position over the steering wheel that allows his reaction time, visual distraction when the driver has not the eyes on the road and he's not aware of the changing conditions of the environment, and cognitive distraction when the driver is not concentrated on the driving task. In all the cases, the distraction signals are not only present in the driver behavior, but also in data related with the vehicle and the road. Hence, the development of a complete alert system must consider these three elements on traffic safety. That is, if we want to predict the driving risk, classifying the driver behavior, we need to make a risk model considering these three elements. Which leads us to the main objective of this work, the development of a robust recording device that allows the storage of data related to the three main elements involved in traffic safety at the moments prior to an accident. All the data acquired with this device will be used by traffic safety experts for the study and analysis of traffic accidents. Okay, this is a general scheme of our system. It could be divided into two main parts. The hardware part, that is in charge of the acquisition of the data that is going to be installed inside the vehicle cabin, and the software part, that it is used by traffic safety experts for the reproduction of the driving sessions captured with the hardware part. Inside the hardware part, there are three systems working in parallel for its complete operation. The acquisition system, that is in charge of the acquisition of data from multiple sources, the storage system, that is in charge of the storage of the data in the correct place, and the data recovery system, that is in charge of keep the data sequences after a traffic accident is detected. These three systems were implemented inside a vehicle computer seated by the GMB company. The computer is controlled by an ARM processor running under Linux. It comes with several USB interfaces that allows the connection of a wireless adapter and a Bluetooth radio for its communication with the acquisition devices. For the acquisition of the internal environment of the driver, an IP camera was employed in order to acquire image from the driver's top view. An omnidirectional microphone was employed in order to acquire sound from the vehicle cabin. And for the external environment, an IP camera was selected in order to record image from the road. Finally, a serial to USB converter was employed in order to acquire data from the vehicle through the bus scan. Inside the wireless black box, there is an independent memory for each acquisition device. All the devices and the wireless black box could be easily installed in any vehicle cabin without interfering with the driver or interfere with the driver task. The internal IP camera was equipped with infrared illuminators in order to acquire image of good quality in any light conditions. After each driving session, all the data acquired and stored in the wireless black box could be transferred to a personal computer in order to reproduce the driving sessions. For that purpose, an accident analysis tool was developed. Okay, this tool that you can see in the video allows the reproduction of the driving sessions in different speeds and in forward and backward direction. It allows the user to make annotations, to add marks, to measure the driving risk, and other analysis functions. It has two types of visualizations. The real-time view, that is the one that you can see on the video, and the detailed view that presents all the acquired data in form of table, so the traffic safety experts can look for changing a specific variable at specific times. In order to facilitate the configuration of the system, only the quality parameters were left to the user. The quality parameters will establish the amount of information that will be stored inside the black box after each traffic accident. For the purposes of our work, we select the medium configuration. In this configuration, we can store driver audio and vehicle data for more than 20 minutes and 15 seconds of video from the road and from the driver. For the validation of the system, all the system was installed in one of the most advanced truck simulators in Europe. The data acquisition considered three simulated scenarios, three of the most common simulated scenarios, urban, interurban, and mountain. Each scenario involves real traffic and interaction with other vehicles. Further, in order to increase the probability of acquired traffic accidents, several risky situations were introduced. These situations, like a group of cyclists, a parked car, a pedestrian with a dog, or a traffic jam, a maintenance area, or a group of rocks, were designed to induce risky situations, but a bad behavior of the driver or a delayed reaction is needed in order to reach this incident into a traffic accident. A traffic accident in this study is considered when the driver hits another object of the simulated scenario or when the driver leaves the road. A total of 8 drivers participate in our acquisition experiment. Each scenario with a length between 15 and 20 minutes was executed by the driver twice, in a first and a second round. This table shows the length of each exercise executed by each driver, and the driving sessions related with traffic accidents are marked in bold. As you can see, not all the driving sessions were related with traffic accidents. This is because the predefined risky situations that we induced were not accidents, were incidents. After each driving session, all the data stored in the wireless black box was transferred to a personal computer and reproduced to a group of traffic safety experts. His main objective was to find out the main causes of each traffic accident recorded with our system. It was found that all the traffic accidents acquired could be labeled with one of the categories in which the driving risk is divided. This table shows the label assigned to each traffic accident. These are the percentage obtained. In first place, the manual distraction was the most common cause of the accidents that we record, and the second most common factor was the visual distraction. Hence, with a proper system inside the cabin that encouraged the driver to have the eyes on the road and the hands on the steering wheel, will have prevented more than 80% of the accidents. Okay, the conclusions of our work. We have presented a novel accident analysis system that was designed to be installed without disturbing the driver. The system was tested in a highly realistic truck simulator, and each traffic accident acquired was analyzed by a group of traffic safety experts. In all the cases, coincidences in the expert descriptions were found. The tool results useful for the generation of a driving risk ground truth, and the representation has enough quality to test different systems inside of the visual representation before putting it on a truck cabin simulator. This is the end of my talk. Thank you for your attention.
So there's lots of time for questions. No questions? Okay, I've got one, for sure. You did not test your system in reality by equipping real vehicles and let people drive with such a system. Do you really think that people want to use this system? Because then there will be video, audio data showing that maybe they made a mistake just before an accident happened?
Okay, this system is thinking for be used by instructors or not in the real life. We are not thinking to install this system in each vehicle, where some countries have some problems to have cameras inside the vehicle. So we are thinking on simulators or specifically in data acquisition cars.
Okay. Can still see no questions. So then we can now close the session 10 minutes earlier than expected. And I leave you all to the following poster session. But first, let's thank all the speakers again.